Welcome to the video lecture series for Texas A&M University course Math 150. Today we will look at section 6.1, Law of Sines, and 6.2, Law of Cosines. You can find the accompanying handouts at bit.ly/RayleneMath150. Let's begin. We're going to look at extending right triangles into the non-right triangle family, or the obtuse triangles. So obtuse triangles are triangles that do not contain a right angle. In general, we can find the area of any triangle using one of these three formulas. Actually, this is the same formula, just with different rearrangements. So let's draw a non-right triangle, like this, for example, and label the vertices A, B, and C. We're going to use capital letters for the vertices, and for the length opposite each angle or vertex, we will use a lowercase letter. I'm going to make my C a cursive or script C because it's hard to tell lowercase c from uppercase C. We can also identify the altitude or the height of a triangle by taking one vertex and drawing a perpendicular line to the opposite base. So for example, if I wanted to find the altitude from point A to this base, I would perhaps have to extend this, and then my perpendicular line would be outside the triangle. So I could have this altitude to the base along the line BC. Similarly, I could go from point C to this base, and I would need to extend my line this way and draw a perpendicular line from the line AB to the point C. And so I would get an altitude something like that. Okay, but we'll stick with the red altitude. It's nice because it's contained inside the triangle. It's a little easier to see. Okay, so if we want to come up with the area of a triangle, in the past we've known that the area is height times base. Well, if I knew that this base was called, let's call it a length of m, and this distance was a length of n, we know that m plus n would equal the length of b. And therefore the area of triangle 1, in the past we would have said is 1/2 the base times the height, which would be 1/2 m times h. And the area of triangle 2 would be 1/2 its base times height, which would be 1/2 n times h. So therefore this is triangle 2. Therefore the entire area of the triangle 1 and 2 would be 1/2 mh plus 1/2 nh, which we could see as 1/2 times m plus n, all times h. But of course, m plus n is nothing more than, in this case, the length of b times h. And if we take a look at h, we can see that from triangle 1, it is the opposite to angle A. And as a result, we could make an equation that says the sine of angle A, now I want to be clear, A here is standing for area, whereas A here is standing for angle A. Maybe I'll label that theta as well. And so the sine of angle theta is the opposite over hypotenuse, which is h over c. And so we could rearrange this to say that h is equal to c times sine of theta. If we take this and substitute it in for h over here, we get that the total area, or area of the entire triangle, is 1/2 b c sine theta. And so theta was the angle A. And so we see that if we are using an angle of A to work out the area, then we need the two sides that are adjacent to it to calculate the area using this formula. In the other rearrangements, if I know lengths A and B, then I would have to use angle C as the angle in between. Or if I knew lengths A and C, then I would require the angle B as the angle between those two lengths. All right, let's go ahead and take a look at showing that the altitude of the height is C sine A. I guess we've just done that. It wouldn't hurt to draw it again. So maybe pause the video, you try this without looking back at the previous slide. So here's a non-right triangle, ABC, and the lengths are given. And the formula for the area I'm going to call this angle theta as well. So the formula for area, I think this is the reason why I spelled the word out area here as opposed to use A, because A also represents the angle, and A for area and A for the angle are two different things. So if we start off with 1/2 BC sine of angle A, which I'm actually going to call theta now, let angle A equal theta. Then we can see that C sine theta would produce a distance here. If we make that triangle, therefore sine of theta is equal to h over c, and c sine theta is equal to h. So we can take the c sine theta and group it, and we can get area of 1/2 base times the height of the triangle. Okay, another word for height is the altitude, and it's specifically the length from a vertex to the opposite base, if you will, drawn perpendicularly. So this way, this dashed line does not represent the height of the triangle, or the altitude from point B to the line AC. Okay, so we can see that we have that area. So this is a special case area if we are not involving the angle, but we know this perpendicular or altitude length. So the law of sine says it's a formula that can be used to determine one missing piece of information out of two sides and two angles. And we need the two angles to be opposite the two given sides. So the formula would be sine of one angle divided by the opposite length equals sine of another angle divided by its opposite length. We could use any rearrangement, but let's just focus on one arrangement since they are all the same thing. We have four pieces of information, two angles, capital A and capital B, and two lengths or sides, little a and little b. If one piece is missing, and therefore we are given the other three pieces of information, then we can solve for the triangle. In the event that two angles on one side are known, so that we have angle, angle, side, or we have angle, side, angle, and by that I mean angle, angle, side would be knowing this angle, let me call that theta, we know another angle, let's call it beta, and we know a side length, let's call it L. So this is the AAS, angle, angle, side case. Or we could have the angle, side, angle case, in which case we might know an angle here, we might know a length here, and we might know an angle afterwards. So these are in order: angle, side, angle, side, angle, side. We know angle, side, angle. In this event that we have angle, angle, side, or angle, side, angle, the triangle can be uniquely determined. Therefore, that means in this case we would be looking for the length opposite B, and it will be solved uniquely. There will be one solution. Similarly, in this case, we have missing angle, but we can solve for that angle as, let's call it alpha. As soon as we solve for alpha, we have one opposite angle side pair, and we can solve either for this missing side or this missing side. In this case, we are going to get one unique solution. However, if we happen to be given two sides and one angle in order, the information may cause us to find no solution, and therefore it would be impossible to make a triangle with the given information. Or it's possible that we might have one solution where only one triangle can satisfy the given information, and it's also possible to get two solutions where two different triangles could satisfy the information. So let's take a look at what a question might look like involving the sine law. Exercise 2 says for triangle PQR, the angle Q is 30 degrees, the length Q is 25, and angle R is 10 degrees. Solve the triangle. I don't worry so much about making sure that all of the lengths and the sides and the angles are correct, but it wouldn't hurt to try to do that. I'm going to draw a triangle like this. It's not a right triangle. We have angle R is 10 degrees and angle Q is 30 degrees. So if I try to find the smallest angle and call that R, and my medium angle is Q, We, of course, could find the missing angle if we wanted to, because the sum of degrees or angles in a triangle is 180 degrees. And we have 40 degrees here, so that means 140 is remaining, and that would be at point P. Then we also know the length of Q, which is 25. And so when solving the triangle, we want to find the missing information. So the missing information is P, which we've already solved for, length R, and length P. So I'm going to use the sine law first. Of course, I have to use the information at Q because it is the only length angle, opposite angle pair that I have. And so I'm going to set up my sine law equation to say that sine of Q over length Q is equal to, well, in this case I can solve for length R or length P. Since I was given angle R, I'm going to start off with that one. And from here, I have information for everything except for length R, so I'm going to solve. One thing I can do to solve is to reciprocate both sides of the equation. And then I recognize that my unknown is R, which is being divided by something. And so I can multiply both sides of the equation by sine of R, which will undo and help me to solve for R. So R is going to equal sine of R times Q divided by cosine of Q. I'm going to put the Q in front. So Q times sine of R divided by sine of Q. And so here I have that R is equal to 25 for Q times the sine of 10 degrees divided by the sine of 30 degrees. Well, I know the sine of 30 degrees is 1/2, and dividing by 1/2 is like multiplying by 2. So 25 times 2 is 50, and I just need to work out the sine of 10 degrees. This, however, would be an acceptable answer without a calculator. Well, let's see what we get with a calculator. So 50 times the sine of, I said I had 10 degrees. Now I believe my calculator is in radian mode and I don't want to take the time to change it. So I'm going to manually convert 10 degrees into radians by multiplying by pi radians divided by 180 degrees. Of course, pi radians divided by 180 degrees is equivalent to 1. And when we convert this, we get 8.682. Let's just round to one decimal place unless otherwise specified. So we have approximately 8.7 units. We can repeat the process to solve for length P, and I'm going to set up the equation directly to solve for P. I could reciprocate the equation from the beginning, and I know that P is going to equal to Q times the sine of P divided by the sine of Q. So rearranging directly, I can find length P as 25 sine of 140 degrees divided by sine of 30 degrees. Again, sine of 30 is 1/2. 25 divided by 1/2 is 50, and so P is equal to 50 sine of 140 degrees exactly, or approximately equal to 50 times sine of 140 degrees multiplied by pi radians divided by 180 degrees gives approximately, I don't know if I hit approximately, 32.1 units. And so we have the triangle. We could find the area of the triangle if we wanted to, but for now solving the triangle means to solve for all of the missing lengths and angles. In exercise 3, we have another triangle PQR. The acute angle Q is 30 degrees, and the length is still opposite angle Q is still 25. But now we're going to look at 3 different cases of values for R. And we're going to solve for R. If we solve for R, of course, we could solve for the missing length P and angle P. But we're only going to focus on R for now, and otherwise we would just repeat the process we saw in exercise 2. In each case, we want to set up an equation to solve for R, like we did here. And then we want to interpret graphically and solve for R if possible. Rather, we have, this is a bit confusing. we want to solve for r, the angle. This should be a capital R, not a lowercase r. So we're given the length r, and now we're solving for the angle r. So unlike the previous question where we had the information that we were given, I'm going to highlight it in green. We were given, well actually I'm going to highlight it in yellow. All of the yellow information was given. And so when we look at this, we have side, angle, angle, or in the reverse order, we had angle Q, angle R, and length Q. And if we just go back to the previous slide, angle, angle, side is a unique case with one solution. But in the current case, we are given an angle, a length, and a second length. So if we draw that triangle, let's call this Q at 30 degrees, length Q, and angle R, and length R is, in the first case, 40. So here we have angle side side, or going back 2 slides, we have side side angle. So in the case of side side angle, we may get no solution, one solution, or 2 solutions. And exercise 3 will explore those 3 possibilities. So using the sine law, or the law of sines, we can solve for angle r as opposed to side length r as follows. We know that sine of angle r is going to equal, over r, is going to equal sine of angle q divided by length q. And we can multiply both sides by length r to isolate sine r. So for now we have sine of r is equal to r times sine of q over q, which is 40 times the sine of 30 degrees divided by 25. Of course, the sine of 30 degrees is a half, and 40 times a half is 20. So we get 20 divided by 25, and we can reduce or simplify this fraction by dividing a 5 out of the top and the bottom. So 5 goes into 20 4 times, and 5 goes into 25 5 times. What I'm asking for now is to set up an equation to solve for r. There is our equation. Interpreting that graphically says if we have the equation sine of an angle is equal to 4 over 5, then that's the intersection of 2 functions, y equal to sine r and y equal to 4/5, where r is like the x-axis. So in this case, we draw the sine graph, and we have to think about what are the possible values for angle r. Well, we know in general that angle r cannot exceed 180 degrees, because that's the sum total of angles in a triangle. We also know that r cannot be negative, because it doesn't make sense to have negative angles in a triangle. We also cannot have r equal to 0, because if we have one angle being 0, then we do not have a triangle, we have a biangle. And so we know that in general, the domain of this equation is going to have r contained from 0 degrees to 180 degrees. But now, already knowing the value of q, we know that there's only 150 degrees maximum left to be shared between angle P and r. So r cannot exceed 150 degrees. So angle r has to be contained from 0 degrees to 150 degrees. So we're going to draw this graph, but only from 0 to 150 degrees. Well, I'm going to take my sine graph like this. That's 360 degrees. That's angle r, and that's y. That's 180 degrees. But as we said, we only want to go to 150 degrees. So we're going to focus on the red graph. And then we're going to intersect with the line y equal to 4/5, which it's hard to know exactly how high up that is, except we do know the height of this point. We know that this point is 150 degrees, which is positive for sine in quadrant 2, with a reference angle of 30 degrees, so it's a y-coordinate of 1/2. So maybe I need to draw it a little bit further down. Maybe 150 is a little bit too far, too close. So 150 degrees is about here. and therefore our height y equal to 4/5 is a line like this. And interpreting here graphically, we see that there are two solutions. And so we have to find the two solutions as we were solving in 5.3, solving trigonometric equations. So to do this, we would say the reference angle, our reference, is sine inverse of 4/5, and we have angles in quadrants number 1 or 2, so that the two possible values for r is the quadrant 1 angle, which is 0 plus the reference angle, or simply sine inverse of 4/5, or r in quadrant 2, which is pi or 180 degrees minus the reference angle. If we were to consider a picture here, what we're saying is that we could have the length r here, we could have, given this length r here, we could have an angle of, let's see approximately how many degrees that is. Calculating the sine inverse of 4/5, and that will be in radians still, so I'm going to convert radians into degrees. And approximating, that gives me approximately 53 degrees, and so 180 minus that will give me approximately 127 degrees. So in this scenario, my two pictures might look like this triangle, where we have approximately 53 degrees here, or I might have a second triangle here, which preserves the 25 along here, but gives me a different angle of approximately 127 degrees in green. So I'm keeping the same r value, the same r length, the same q angle, the same r length, and the same q length, but my r angle is changing from either 53 degrees or 127 degrees. So those are my two solutions, approximately 53 degrees or approximately 127 degrees. Let me just draw this triangle again so you can see. R at 53 degrees, and this triangle doesn't look so good. I'll try it again. R at 127 degrees. Okay, in the next case, part B, we want to start off with the same information about length q and angle q, but r is now 50 for the length. So in part B, I'm going to start off with the same kind of diagram. It may or may not be realistic, but the math will help me to see the solution or not. So I have angle r here, which is unknown. I have length q, which is still 25, and I have length r, which is now 50. So in this case, we start off again with the sine law, and we will interpret the equation graphically. So we will have that the sine of r is equal to length r times the sine of q divided by length q, which is 50 times the sine of 30 degrees divided by the length of q of 25, and that's going to give me 50 times 1/2 divided by 25, which is 25 over 25, or 1. Again, we know that the angle r has to be contained from 0 degrees to 150 degrees, and if we think graphically, we know that this graph can only have one solution that intersects with a height of 1, and that angle corresponds to 90 degrees. So our system of equations that we would be solving, of course, is y equal to sine r in red, intersected with the graph of y equal to 1. And so here we see clearly of the SSA case, which is the ambiguous case of no solutions one solution or two solutions, we have one solution, and the one solution specifically means that angle R has to be 90 degrees. So this is when Q is 25 here, and I can refine my diagram by saying that angle R is 90 degrees. In the last case, part C, we're going to take R equal to 60 degrees and see what happens next. Why don't you pause the video and try it for yourself. So filling in the information, we have length R is 60 units, length Q is 25, and still angle Q is 30 degrees. So again, from the sine law, we have that the sine of R is equal to length R times the sine of Q divided by length Q. So we get 60 times sine of 30 degrees divided by 25. Sine of 30 is a half. Half of 60 is 30. And 30 divided by 25 reduces to the fraction 6 over 5. So what we have is sine of R is equal to the ratio, the opposite over hypotenuse ratio, of 6 over 5. And right away we know that this is going to be an invalid ratio, which is going to lead to a non-real angle. The reason we have a non-real angle R is because when we look at the system of equations, y equal to sine R, which is a bounded function between the heights of -1 and 1, but specifically on the domain of R that we are using, we know R has to be contained from 0 degrees to 150 degrees. This graph is not only bounded from -1 to 1, it's in fact bounded from 0 to 1. And we are going to intersect that function with a horizontal line at a height of, let me make this a little bit higher. The horizontal line is at a height of 6 over 5, which is greater than 1. And as a result, there is no intersection point, there's no graph, so we have non-real as opposed to undefined result. And so we see that we have no solution. And so what we're finding is that it is impossible to close off a triangle with this length. And if it's impossible to close off the triangle, then the length that we are solving for, which is R, is just not going to be long enough to work with the information given. We simply won't be able to close off the triangle. Rather, in this case, it's the Q which is not going to be long enough to close off the triangle. And so we have no solution, no triangle possible. All right, moving on. Exercise 4 asks you to solve the triangle with the given information, and it says show that there is no triangle in part A, solve in part B, and in part C it says to solve for the two triangles. I'm going to leave you to do exercise 4 on your own as a homework assignment. Now we're going to continue on and look at the cosine law. In the sine law case, just to review, the law of sines, or the sine law, started off looking at information of two sides and two angles. And we had to find a missing piece of information. In the case of the law of cosines, this is a formula used to determine when we have still one missing piece of information out of 4, but in this case, the 4 pieces of information that we are interested in or dealing with are 3 sides and only 1 angle, as opposed to 2 and 2 for the sine law case. So the different rearrangements of the formula are written here. We're going to use the cosine law to try exercise 1. A racing committee wants to lay out a triangular course with a 40-degree angle between the two sides of 3.5 miles and 2.5 miles. What will be the perimeter of the course? Could you use the sine law in this case? Explain. Well, let's draw a triangle. I almost always draw my triangles like this for the oblique or non-right triangle pictures. And I'm going to say I've got one length of 2.5 miles, and another length of 3.5 miles, and we're told that the angle in between is 40 degrees. So I think what I'm going to do is call this angle ABC, and then opposite angle C we have length C, and opposite angle B we have length B. If we want to find the perimeter of the course, we need to solve for length A. In this given problem, we have two lengths and one angle, and we are interested in finding the third length. So of the sine law information, two angles and two sides, or the cosine law information, one angle and three sides, we have the information from the law of cosines. So it is not possible to use the sine law in this case. The reason is we don't have one of the angles opposite either length C or length B. Okay, so we go ahead and we say that we want to solve for A, so we're going to use the version or the rearrangement for that side with the corresponding angle. So A squared is equal to B squared plus C squared minus 2BC times the cosine of angle A. And we have B is 3.5, C is 2.5, and C is 2.5 times this 2 is going to give me 5 times 3.5 times the cosine of angle angle A, which is 40 degrees. And so we can type this into the calculator and get a value for A squared. So let's just make this a bit smaller so we can see underneath. So we have 3.5 squared plus 2.5 squared minus 2 times 2.5 times 3.5 times the cosine of 40 degrees. I am still in radian mode, so I'm going to manually convert degrees into radians by multiplying by pi radians divided by 180 degrees. And I will approximate that value to get 5.09, approximately 5.1 for the value of A squared. In fact, I don't really care to know what A squared is, I want to know what is A. And so I'm going to take my result and square root it. Notice that I'm collecting the number prior, which wasn't yet rounded, as opposed to simply typing in the square root of 5.09. It makes a little bit of difference in the rounding, so please don't round until your final answer. So I'm going to use 2.257, but then I can round that to 2.3. So I'm going to say that A is approximately 2.3 units, and therefore the perimeter of the course is going to be 2.5 plus, is approximately 2.5 plus 3.5, which is 6, plus 2.3, which is approximately 8.3 miles. In exercise 2, we are asked, what famous formula does the cosine law simplify to if one of the angles is 90 degrees? So if we draw our picture like this, we have A, I'm going to put B here, C here, and then this is length C, this is length B, length A, and we're going to let C be 90 degrees. If that's the case, then the cosine law says we always start off writing the cosine law from the point of view of the side that is opposite the angle given. Whether or not we know this side or don't, this is the first letter that we have to write in the cosine law case. So C squared is equal to A squared plus B squared minus 2 times these lengths of A and B times the cosine of 90 degrees. And from the cosine graph, we know that the cosine of 90 degrees is 0. And so we have C squared equals A squared plus B squared minus 2AB times 0, which is all 0. And so we get C squared equals A squared plus B squared, which of course is the Pythagorean theorem. And the way it is written, we know that C has to be the largest side of the triangle, which it is, and it's given the special name of hypotenuse when the angle opposite it is a right angle. So when it comes down to knowing only one formula, which is the more general formula, the cosine law or the Pythagorean theorem? In other words, which is the special case of the other? We know that the Pythagorean theorem is a special case because it's valid only when one of the angles is 90 degrees. So if you were to only memorize one of these two formulas, make it the cosine law. This is the general version. Of course, it's probably impossible to unlearn the Pythagorean theorem, but you can memorize the cosine law as an extra bit or an extra term that's different from the Pythagorean theorem. Another formula we want to look at is Heron's area formula. And so instead of using the previous formula, which we said area is 1/2 times one length times another length times the sine of the angle in between them, so if this is B, this is C, and theta is in between, we can come up with another formula for area, which involves calculating the half perimeter. We are going to say that length A plus B plus C of the triangle divided by 2 is S, the half perimeter. And then Heron's formula says that area is equal to the square root of S times S minus A times S minus B times S minus C. So using this formula, or just discussing it, in exercise 3, if the units of the side lengths of the triangle are in meters, what are the units of S, the half perimeter? We know that each of these is measured in meters, and 1/2 isn't going to change. So 1/2 of something measured in meters will give units of meters. And when we're looking at the area formula, we're going to get something measured in meters times something measured in meters times something measured in meters times something measured in meters, which is going to give us the square root of something measured in meters to the exponent 4, which is meters squared. Now area doesn't equal this. I'm going to use an arrow to represent that area implies these units. All right, so one last example. Determine the area of a triangle with side lengths of 1, 1/2, and 3/4. We could use the formula that we saw in section 6.1, which said 1/2 AB sine of theta, where we have A and B here and theta. But then we would actually have to use the cosine law to work backwards to find the angle first. Instead, knowing just the 3 lengths, we can use Heron's formula, which says that area is equal to the square root of S times the difference, the product of the half perimeter minus each length, all multiplied together. Maybe I didn't say that right. So the first thing we do is calculate the half perimeter. And we get 1 plus 1/2 plus 3/4, all divided by 2, or 1/2 times. Getting a common denominator, we have 4/4 plus 2/4 plus 3/4. So 4 plus 2 plus 3 is 9/4, and the half perimeter is 9/8. So therefore area is going to equal the square root of 9/8 multiplied by 9/8 minus A. I'll take the first value, A, to be 1. I'll take B to be 1/2, and I'll draw it in a different color. And A is 8/8 for the purpose of getting a common denominator. B of 1/2 is equal to 4/8, and C is equal to 3/4, which is 6/8. So I'm just going to substitute the numbers in directly. S minus A is 9/8 minus 8/8, which is 1/8. S minus B is 9/8 minus 4/8, which is 5/8. And S minus C is 9/8 minus 6/8, which is 3/8. And from here I see that I have 64 times 64 in the denominator, coming out of the square root, gives me only 164. And then in the numerator, I'm left with 9 times 15. The 9 can come outside of the square root as 3 square root 15 divided by 64. Well, that completes 6.1 and 6.2, the law of sines and the law of cosines. Please make sure that you have completed the handout and prepared a list of clarifying questions about the lecture. That's all for now.